All right. So today, momentum, kids. Momentum. All right. So a big fat guy like me comes running at you. Okay. Let's say I'm doing like 30 mile an hour, which might be a joke because that'd be hard for me to get going that fast. But if I did get going that fast, friends, I'm gonna keep going that fast. Are you with me? Why is that? Because I got a lot of mass. Okay. A little tiny bullet. Okay. It also has quite a bit of momentum. Even though it has no mass to speak of, it's got a huge amount of velocity. Momentum is P. Okay. Why not M? Because mass. Okay. Momentum is mass times velocity. Always. Groom, does that mean it's going to be measured in kilograms, meters per second? That's correct. Or some people write it as a Newton second. I'm sorry, Newton second. A Newton second. Now, what does that mean? Well, remember, this is kilograms, meters per second squared times a second, and you get the same thing, right? But typically, Groom's going to write it as kilograms, meters per second. Okay? And that's all there is to this thing. This is a vector. How do I know it's a vector? Because velocity is a vector, sir. That's how I know. Well, what are you saying? I'm saying that your velocity is going this direction. I times it by m, how much mass you have. And let's say if this is you and you have 100 kilogram of mass, and this other fat guy has 200 kilograms of mass, you see his momentum will be twice as long as yours. Yes? If you had the same velocity. Okay? We call that mass, we call it a scalar. Okay? It scales, it makes it bigger. That's all we're talking about. Okay? And so it's pretty straightforward. So, what would happen if you had a running back run in this direction? 30 kilograms, little fella. Oh, all 100 pounds. No, all 60 pounds of him. Well, we were making a little fatter than that. All 70 kilograms of him. Yay. And he's running it at 15 meters a second. He's hauling ass. Woo, doggy. And here comes his linebacker coming this way. Whoa, Groom. Yes, he weighs 100 has 100 kilogram mass, but he's only going 8 meters per second. What's going to happen? Well, they are, as you know, vectors. And so how do you add vectors? Well, you add them tail to head, yes? And so if you get your calculator out, I'll do the hard one, 800. And you do the hard one there, 75 times 70 times 15 is 1,050. And so that means if they hang on to each other, we call that an inelastic collision. Okay? Now, whether they bounce off or not, in the real world, every collision is, for all intents and purposes, what we call an inelastic collision. What happens is momentum is always conserved. Okay? That means the amount of momentum initially is the same as the momentum afterwards. Okay? So in this case, I'm going to wrap them up and we're going to fly out of bounds this direction. Okay? That's the direction we're going to fly off in once we hit each other. We're going to hit here. We're going to fly out this direction. That direction. Okay? That's the idea. Okay? Now, how we did it was a squared b squared c squared, of course. So 1,050 squared plus 800 squared is that. And take the square root of that. Oh, for the love of Mike. You get 1320 is the total momentum, yes, in this direction. What direction is that? Well, that's a good question. Could I find this angle? I bet I could. I bet it's arctan. Arctan of 800 rather, over 1,050. About 37 degrees. Are you with me? Okay. How fast will we be traveling? Well, our combined mass is now 170. So 170 times v is equal to 1320. So it looks like we will be traveling now at 13. Oh, for the love of Mike, about 7.7 meters per second. Okay. Yeah, and the crowd goes wild. Now, clearly, in a situation like this, when the two become one, it's actually a way easier problem. How do I know that? Well, because we are just, there's one thing to track. That doesn't have to happen that way, though. In fact, you could have a situation where you've got a ball coming in like so, and then another ball coming in like so, and they hit. And then this one maybe kind of comes off this direction. This one kind of comes back off this direction, or whatever. Is there more stuff to keep track of? Yeah, a little more stuff to keep track of. Is it a big deal? No, not really. And so here we go. I'm going to say this ball, this is viewed from above, is coming this direction. And he is hit by a ball coming this direction. This one has 10 kilogram mass, 3 meters per second. This one is 8 kilograms, 7 meters per second. Afterwards, this one afterwards is coming like thus. This angle here is 40 degrees. This angle here afterwards is 20 degrees. This one is now, this guy is now doing 6 meters per second. What's the other guy doing? Can we figure that out? And the answer is yeah, we totally can. So afterward, well, we have, if you will, this is initial momentum 1, initial momentum 2. So P1 plus P2 is the total momentum, yes? But that will be equal to P1 new plus P2 new, right? Because momentum is always conserved, okay? And so it's really pretty straightforward, okay? So when you look at this problem, it's like when we did displacement earlier, we added displacement vectors. It's very similar, okay? We have to break them into pieces. So here we've got 56 kilogram meters per second for this fella in this direction, yes? This guy is 30, right? But then we have 30 this direction, 30 sine 40, 30 sine 40. So 30 sine 40 is 19.28. That's in the vertical direction. 19.28. I swear. And then the other one is cosine 40. Oh, for Pete's sake. Cosine 40. And 22.9 in this direction. Okay? Which means that what I've got is, so plus 22.9, and then I've got this down, so that's this direction. And I got 19.28 this direction. You with me? Done. Okay, which means that my total is thus, yes? Make sense? So when I do that, of course, I'm going to get plus 56 is that, squared is that, plus 19.28 squared, and then the square root of that, 81.3, and I would like to have that angle too, if you don't mind. So inverse tangent of 19.28 divided by, I didn't add that up, did I? 78.9. About 13.7 degrees here, are you with me? Nice. Lovely. Okay. So that right there is your total momentum. Okay? Before. Okay? It's going to be our total momentum after, too. So what I said was this cat is now going 8 meters a second, but at a 20-degree angle. Are you with me? So that's 48 cosine 20. Oh, for the love of Mike. 48 cosine of 20 is 45. So that's 45 here. And then we're going to be able to do sine too. And you get 16.4. Now, Groom. Wait a minute. Groom, what's happened here? Well, now watch what's happened here, bud. Initially, you'll notice we had 19.28 downwards. You with me? We currently have accounted for 16.4 of that. And that means this other ball didn't bounce up. It must be doing what? It must also be coming downwards. You with me? Whoa. Like how much? Well, I don't know. Let's do some math. 19.28 minus 16.4 leaves us with 2.88 downwards. The other ball must have that. Are you with me? And notice also that we had 78.9 this direction. Yes? Right? In this direction. Well, cool. We've already got 45 of that. So the rest of that must be with the other fella. Right? And so if you do that, 78.9 minus 45 is, damn it, minus 45 is, doggone you, you hippie, 33.9. So 33.9. Okay, there you go, friends. So if I find that piece there, 33.9 squared plus 2.88 squared is this. And if you square root that, you get 34 point whatever I said. Okay. Well, how big is that guy now? Okay. Well, that guy is still 10 kilograms. Yes? Still 10 kilograms. So 10 times V equals 34. 10V equals 34. 34. So that means V is equal to 3.4 meters per second. Okay. So what ended up happening is this one ended up speeding up a little bit. This one ended up slowing down a little bit. Now, I made this angle up. Are you with me? I made it up. I made it up. So that means why this problem's a little weird. But the math has to work every time because momentum before has to equal momentum after. Every time you take it to the bank. Okay? Take it to the bank. Mr. Groom, what would happen if you saw, well, okay, true story. Hardest hit I ever saw, freshman year of college, is on a punt return, and our guy Jimmy Beck is going down to cover it. Jimmy Beck's nuts. Okay, he is flying like a bat out of hell. He's about 6'1", 225. He can fly like the wind. Okay, and this guy caught the punt and he put his head down, took like one step, and Jimmy hit him. And this is back in the good old days when you could, all right, here I got the ball here like this. Here comes Jimmy launching himself. But that's targeting. Well, whatever, bro. I don't know what to tell you. Lots of momentum. Very little momentum. And then the next second, they're like this. And the other guy's kind of like this. And then, wham, into the ground. And it was intense, to say the least. Jimmy got up, took 2 steps, flopped back on the ground. He was down and walking like the funky chicken. He got up again. He kind of wandered off the sideways. By the way, did we go back in the game? Of course we went back in the game. We all got concussions. No one cared about him back then. The other kid, they carted him off. But hard hit. Okay? Groom, what are you saying? Well, I'm saying, first of all, I'm saying it was a hard hit. It was an amazing hit. So this would be like 100 kilograms. I don't know, 15 meters a second. He was hauling. But this kid, 70, 80 kilograms, sure. And he was going 2 meters a second. Okay? How much total momentum was there? Okay, well, they're going opposite directions initially, correct? And so if you do that, that's 1,500 minus 160, right? 1340. 1340 kilogram meters per second initially. Well, that's what it's going to have now as well, yes? Okay. And so what now the difference is you have 180 times V is equal to this guy. And so divide by 180 is 7.4 meters per second is how fast they're traveling backwards, okay? Easy stuff. Easy money. Momentum is one of the easier topics there is to do and understand. It's just simply a matter of adding vectors and adding them correctly. Okay? All right. Now, later in this chapter, never mind. So let's say there's going to be a collision here. This car weighs 2,000 kilograms. Sure. 30 meters a second. Awesome. And this car here, it's a truck, let's say, 3,000 kilograms. Okay, and Also 30 meters a second. Well, that's 9, and then 1, 2, 3, 4, 90,000. And then this is 6, 1, 2, 3, 4, like so. Okay. This angle here, 45 degrees. So 90,000 times the sine of 45. And as you know, so this is 63, 639. 63, 639. This is also 63, 639 because obviously 45-degree angle, correct? But that's going this direction. So our total is going to be 60,000 or 63,000. Oh, darn it. 63,639 minus 60,000 leaves us with a whopping 3639 in this direction. 3639. However, we are still 63,639 in this direction because they are vectors and they cannot cancel out. Meaning that for all intents and purposes, when the wreck happens, we're going to fly off this direction. Does that make sense? Okay. In essence, this momentum and this momentum, in essence, cancel out. Not quite, almost. And then this momentum is all in this upwards direction. So there's just mostly upwards and a little bit that way. Yes? And so if you do the math, of course, that's squared plus 63,639 squared to the 0.5 is... What? That's cray-cray. 63,743. 63,743. Now, if they stuck together, which we're going to pretend they did for the sake of argument, that's 5,000 mass, right? 5,000 kilograms. So then divide by 5,000. Divide by 5,000. And so they will be traveling this direction at 12.7 meters per second, right? That's where you will find the stuff over there. Now, some of them might well say, Groom, if that whole thing was traveling that far and it was twisted metal on concrete, can we see how far they should have slid using some friction? Yeah, you're right. We can, bud. You're right. We could absolutely do that. That's pretty cool. What if they became a projectile? There was a cliff right here. You know, it was a cliff, and then the cliff was like, I don't know, like the edge of the Grand Canyon deep. So how far out would they fly? Because they're a projectile. I don't know. We can figure that out too if we want to. Am I right? Of course we could. Okay, we can play this game all day long. In fact, you will be doing a lab. You'll be doing a lab of this, and I'm pretty excited about it. Okay, so we'll be doing something similar to this, not crashing cars, of course, but yeah, similar idea. Okay, nice. We're going to do one more of these guys. Again, we're going to do the two that are very similar-ish in size. 8 kilograms, 3 meters a second. 7 kilograms, 4 meters a second. Cool, they hit. Boom, boom, ba-doom. This guy's coming in at 30. This guy's coming in at 20. Okay. And then let's say that... This guy comes off at a 25-degree angle, okay, and whatever. Then a 25-degree angle, correct. Then what will the other guy be doing? Okay, all right. Let's try that. Just see what happens here. So again, that's 24. This is 30. So 24 sine 30 is 12. 24 cosine 30, I can do it on top of my head. 24 cosine 30 that's 224, stupid, is 20.7. Okay, so we got 20.7 going this way, we got 12 going this way. The other one is 20, and it's 28 here, yes? So 28 sine 20. Oh, you hippie. 9.57, 9.57, that's downwards. and 28 cosine 20. 26.3. So if you're thinking, or not degrees, stupid, is 26.3. So, meaning we have 26.3 plus 20.7. We have 47 in this direction, 47. We have 12 up, 9.57 down. 12 minus 9.57 is 2.43 in and upwards. 2.43 upwards. Yes? And so, can I find this? Yes, of course. So, 47 squared. Come on, give it to me. Plus 2.43 squared. And then to the 0.5 is 47.0 whatever. Okay, basically 47. Okay? And that's cute, Groom. So that's cute. And what angle is that on? Well, I don't know. What angle would that be on, sir? So, and you can leave it like that, or actually I'm not going to worry about it. I'm just going to say there it is. Okay, there it is. Boom, done. Okay? Okay? So if we're coming downwards at a 25 like this, are you with me? Okay. Do I need to know how fast I'm going? I sure do. Okay. Let's say this guy's coming downwards at 2.5 meters per second. Okay. All right. If that's the case, then he now has 8 times 2.5 is, what is that? 20? 8 times 2.5 is 20, isn't it? 8 times 2.5 is 20. Yay! So, I have this new triangle. Again, it's all triangles, dog. I don't know what's so hard about this. So, it's 8 times, so it's 20. And so then 20 cosine 25 is 18.1 up here. And sine of 25 is 8.5 over here, if you will, right? Does that make sense? Right? All right, cool. Well, listen, pal, what you've just done is we know that we've got a total of 47 this direction. That means the other guy has to do 47 minus 18, right? 29. And we know we have a total of 2.43 upwards, right? But we already have an 8.5 down, so if I add them, 2.43 plus 8.5 is 10.93. So this guy has to be going up 10.93. And how do I know that? Because 10.93 minus 8.5 is the total 2.5 up, right? So then the question would then, oh, for crying in the mud. 29, right? 29, right. So then, can I then find this angle? Obviously. Can I find how fast this cat's going? Yeah, of course. So it's going to be 29 square plus 10.93 square to the 0.5 is 31. And so then I would say that guy is going, he is 7 kilograms. So 7V is 31. So V is 4.4. Yay, meters per second. That's the game, okay? We will spend more time with this in the coming weeks. Well, in the coming weeks, I'll make a couple more videos about this. We'll get a little more crazy on it. But that's the gist of it. All right, have some fun with it. Chapter 5.